All right, guys, we're starting Unit 4, momentum. You have the equation P equals mv. Momentum is mass times velocity. Hopefully the positive physics went well, the review, the inquiry, and the definition of momentum. So go ahead and pause the video and try this warm-up. You have 4 different scenarios here with a 1,000-kilogram car and then a 3,000-kilogram car at different speeds. You're just ranking the momentum from least to greatest, something you should be adequately prepared to do. So go ahead and pause the video, try that. All right, so hopefully we can check out this ranking, make sure you got it correct. So 10 meters per second, 1,000 kilogram. The momentum is just 1,000 times 10, so I'm getting 10,000 kilogram meter per second. There's no short unit for momentum. We're just going to have to say kilogram meter per second every time. Next one, mass times velocity, 1,000 times 20, or 20,000 kilogram meter per second. 30 times 1,000. 30,000 kilogram meter per second, and then the last one 3,000 times 10, or 30,000 kilogram meter per second. So it's like A is the least, which is less than B, which is less than C, and D, which are the same, 30,000 kilogram meter per second. Okay. All right. So next thing I want you to do is write down the definition of momentum. This is, I'll give you the book definition, which is always a severe disappointment. They say it's the product of mass and velocity. That's an equation, right? That just says that P equals mv. So if we want maybe a better qualitative definition of momentum, it's inertia in motion. It's an object's resistance to change in motion, and it depends on both the mass and the velocity of an object. So something that's moving really fast or something that's really massive, it's difficult to change the momentum of that object or to change the motion of that object. So inertia was due to the object's mass. Mass is a measure of an object's inertia. Momentum is due to the object's mass and velocity. So it has to be moving to have momentum. The units of momentum, kilogram meter per second, that checks out because the equation is just mass times velocity. But if you really play around with units, we could show that a Newton second, or Newton is a kilogram meter per second squared. When you multiply that by seconds, and here the seconds cancels with one of them on the bottom, you end up with that kilogram meter per second. So there's something weird going on. We will dive into that a little bit further, but it suggests that there might be an additional equation or a relation to momentum. So kilogram meter per second is the typical unit that we'll use. But a Newton second is identical to a kilogram meter per second. So that might be important later. Okay, so P equals mv, momentum is always conserved. So just like energy was a law of conservation, we saw that there were things that could mess up energy, like kinetic friction, things that, non-conservative forces that changed the total energy of a system. For momentum, in all collisions, momentum is going to be conserved, where energy won't, because there's always going to be an amount of kinetic friction when two objects collide. Momentum is still going to be conserved, even if there's kinetic friction between the objects. So we'll talk about cases that do not conserve momentum, and for all collisions, though, we're going to assume momentum is conserved. Momentum's always the way that we want to go when we're dealing with collisions, because most of the forces are internal to the system. They're occurring between the two objects. And that could be a kinetic friction between the two objects, which messes up energy, but it doesn't mess up momentum, okay? So momentum is conserved for all types of collisions. Okay, go ahead and pause the video again. What you're doing here is you are putting yourselves in the shoes of an engineer who's designing a vehicle to be safest on the road. And you have these 4 different options to choose from. And they're designing the cars made of 2 different materials. So you have a very strong metal that is incompressible. So think of like steel, really strong metal, really, really hard and not very pliable. And then the yellow material, which would be more of like an alloy, more of something that is compressible, that can bend, still hard, but not quite as rigid as the incompressible material. So in which orientation using those two materials would be the safest vehicle. So vehicle one, your first option is to have the incompressible material in the front and the back, kind of like to take the impact of a collision in the front and in the back. Number two is putting your incompressible material in the middle section and then the compressible material here and here in the front and the back. Number three, I would say that's kind of like the Batmobile. This is just like fully incompressible, making it just as strong as physically possible. And then number four is to lighten the vehicle, making the entire vehicle out of the yellow material. Then pause the video, decide which you would choose, and then hopefully we get the answer a little bit later. Okay, so you've made your choice, and I want to introduce now impulse. When we think of collisions, we often think about them as being instantaneous, happening for such a short period of time. But all collisions have a measurable amount of time. And the time that an object is involved in the collision affects the impulse. So I have impulse here. We're using capital J, impulse. And the impulse is the force on the object during a collision times the time of the collision. So I have these really nice GIFs here. This is a golf ball at 100 miles per hour hitting a steel plate. And you see the compression of the golf ball. You see the deformation. That's killing energy. Energy definitely not conserved here, but momentum should be conserved for this system. And then you have here a baseball that's hitting at 100 miles per hour against some steel. And you see that compression again. That means that the time of the collision is not instantaneous, right? You could measure the time of collision being any time where the ball is in contact with the wall. Okay, so impulse is force times time. If I look at the units of this, of an impulse, well, force is newtons and time is seconds. So it suggests that there, again, there's some connection here to momentum with impulse, and Newton second is the same thing as a kilogram meter per second. And it turns out that the impulse that an object experiences is equal to the change in momentum of that object. So the larger the impulse, so maybe the larger the force or the larger the amount of time, the greater the change in momentum of the object. So impulse is equal to the change in momentum. So imagine we were doing an egg drop experiment. We dropped 3 identical eggs on different surfaces, but we changed the hardness or softness of the surfaces. Which of the following is true? A, the softest surface will cause the least change in momentum, the least impulse. Hardest surface will cause the least change in momentum. Again, that's the impulse. And then the change in momentum is the same for each surface. Well, think about it. If you drop an egg from some height of h, okay, we could use conservation of energy to find out what speed it hits the ground with. Regardless of what material we put on the bottom that it collides with, essentially the egg goes from a velocity initial of 0. You could figure out the speed that it hits the ground with, and then regardless of what surface it hits, you know the final result is the final velocity after the collision is 0. So what's interesting is regardless of the material that you use, the change in momentum is just going from some velocity to 0. And it would be exactly the same in all cases regardless of the material chosen. But you know the result is different. The softness or hardness of the material affects which one would break the egg. How is that possible if it's the same impulse for all 3 cases? You use a really soft material, a really hard material. So we're going to try it out with a pillow, a wrestling mat, and a concrete floor. And you could probably guess which of these 3 materials is going to allow the egg to survive, even though it experiences the same change in momentum. Imagine you're guessing that the pillow is the one that's going to make the egg survive. Which egg will experience the greatest impulse? Remember, impulse is change in momentum, so they are all the same. Why is it that we survive the pillow, but of course the wrestling mat and the concrete, the egg breaks? If they're experiencing the exact same change in momentum, the exact same impulse, what is the difference? And it comes down to that time of collision. So what happens with the pillow or the softer material is the time of collision is much longer, meaning the pillow doesn't accelerate the egg as greatly. They're all slowing the egg down. They're all bringing it to a stop from its velocity just before hitting the floor, but the pillow cushions that fall a little bit more and makes that acceleration take longer. So if I look at the impulse, impulse is force times time, and I want to calculate the force based on these identical impulses, then I'm going to do the impulse divided by time. So on my calculator, if I take 3 divided by 0.2, I get 15 newtons for the pillow. 3 divided by 0.1, I get 30 newtons for the wrestling mat, and 3 divided by 0.05, or 60 newtons for the concrete floor. So 15 newtons is below the threshold of 24.5. That's the force that would make an egg break. The only surface that goes below that force is the pillow. So our 15 newtons is why the egg survives. But the reason why the force was so low was because the time of impact was so great. So if I think about impulse, and the impulse is identical for all 3, because they all reached the same speed and then were brought to a speed of 0 by the surface, pillow, wrestling mat, and concrete, I can write this kind of suggestively. Even though the impulse is the same, if the time of the collision is very small, then the force would have to be really great for the product of force and time to equal an identical impulse. If you can extend the time of collision, that's what a softer material does, it extends the time of collision, then you can make the force felt be a little bit smaller. So a small force for a larger time of collision. These products give you the exact same impulse. So the reason it survives the pillow but not the concrete is because of that time of collision being so great. Okay, which brings us back to our scenario. I have here the image of all 4 vehicles after a collision. And unfortunately for vehicle 1 and vehicle 4, these are not good. These are not survivable collisions. And that is because we've used the compressible material in the cabin of the vehicle, which means the compartment where people are actually sitting in, there's no room. There's no room for you to survive that collision. So that's unfortunate. That's not to say that there are no cars designed in this way, especially number 4. There are definitely cars designed this way, and you can imagine why they're designed that way. It's cost, right? The cheaper version of a vehicle is this number 4. That doesn't make it the safest version. And I look at vehicle number 2 and number 3, and I look at the compartment where my passengers are. Both of the compartments are full. They haven't been compressed at all, which means there's at least room to survive those collisions. But I am suggesting that one of these vehicles is much safer than the other. If you haven't guessed at this point, it is I think it was our vehicle number 2. Vehicle number 2 is the safer vehicle. This is how a lot of modern cars with safety features are designed. These zones in the front and back are called crumple zones. And they are designed to take the brunt of the impact. So if somebody hits you head on or from behind, these crumple zones are designed to take the brunt of the impact and essentially not to transfer that force or a great acceleration to the passengers. Even though this vehicle looks fine, unfortunately, with such a strong material and all being fully incompressible, the impulse that's felt in this collision is going to be for a very short amount of time, which means it's going to be a great force. And the vehicle with the crumple zones will extend the time of the collision, meaning it takes longer for that vehicle to come to a stop, even if it's fractions of a second. If it takes longer for this vehicle to come to a stop, the force felt by the passengers is going to be much smaller. So while this vehicle looks great in the end, the kinds of injuries that you would see with this type of vehicle, because the force internally is so great, are things like whiplash. You hear about the seatbelt holding you in, but your head flying forward, and that can be Really painful, can be really debilitating type of injury. Now, I'm confident that if you talk to maybe an older generation, somebody in your family, and you describe this slide right here to them, they still might prefer vehicle number 3. They still might prefer the Batmobile, and it comes down to cost. For example, modern vehicles with these safety features with crumple zones, even in a slight fender bender, these vehicles are often totaled and need to be completely replaced. These vehicles, this one that has been in a collision, you could turn around the very next day and you could sell it, and no one would even know that it's been in a collision. Now, for my money, I prefer the safety to the passengers, but again, I know there would be a faction of people out there who might prefer this vehicle just because in the event of a collision, they're not totaling the vehicle. So there is a trade-off with cost and safety. I'm taking safety. Okay. I do suggest that you take a look at the vehicle that you drive and look up the crash tests. It's kind of an interesting thing to see. This is kind of an ideal crash test. This is what you want to see, where the crumple zone is taking the brunt of the impact. All of the cabin of the vehicle is remaining intact, and really the forces that the people are feeling inside aren't that great. We as the engineer who's designing these vehicles, you can't control how fast people are going to go. You can put speed limits, but it doesn't mean that people aren't going to exceed the speed limit. So when I think about this equation, which is what you're doing as the engineer here, you can't change the impulse. You can't change any of these factors. When someone gets in a collision with a wall or a tree or a telephone pole or another vehicle, they're going to go from whatever velocity they're traveling down to 0, and you have no control over that. So what you try to do instead is control these factors. If the impulse is going to be the same regardless of the collision, how can you make the collisions more survivable? And the idea is to extend the time of the collision so that the force felt is much smaller. Again, you have to look at what factors you are able to control. In this case, we're only able to control F and T. I have some examples of some of the other cars here. This is a very old car. This would be like a number 3. It's made of incompressible material. It's very strong. After this collision, you could turn around and sell it. But I really want you to pay attention to that person who was in the back seat and basically ends up in the front seat at the end of the collision. So the forces that are felt here are really great. And this is only like a 40-mile-per-hour collision. So you really see the dummies here get tossed around. Even though this collision doesn't look that severe from the outside, if you look at those passengers, it is very severe, and they would have some pretty significant injuries. And I said, even there are some cars like number 4. So very unfortunately, this is a car made of mostly compressible material, very cheap car, and it does seem to just be disappearing here as it hits the wall. So that's obviously a problem when you don't have any room in the cabin left over for you and your passengers. That's obviously a very, very bad collision. So check your vehicle, see what kind of crash test ratings it gets. You're hoping that it's a number 2 with crumple zones. That is the safest type of vehicles. But now hopefully we understand a little bit about why those vehicles are safer. So that should be it for impulse momentum.